I want to welcome you to my lecture today. Of course, today we're going to be focusing on consistency of point estimator. And of course, this is going to be our final lecture on consistency. Before now, I've walked you through, property of a good estimator. Okay, so I think I'm going to have a recap before moving forward. Why do we, how do we actually find ourselves in a situation where we need to investigate the property of a good estimator? Because initially we want to figure out the true value of parameter. Parameter could be uh, population mean, population variance, population standard deviation. It could be proportion, it could be difference of proportion, it could be difference of means. It can also be a parameter, that is unknown in a given probability distribution, okay, from which a sample of data is to be collected. Now, if we, because we do not have enough resources to study entire population, and because we're limited by budget, of course, we're going to take a sample, and when we take a sample, whatever parameter of interest, there will be suggestion about formula method that we call estimator. Okay, so how are we going to know if the estimator is going to do a great job? Okay, so one of the reasons why statistics is very, very interesting is we got a way to figure that out. So in this class, I've walked you through property of estimator, like unbiasedness, like efficiency, and of course, the last time we met, we actually did consistency. And of course, in this lecture, we're gonna finish, the consistency as one of the property of a good estimator. Okay, so in today's outline, of course, we're focusing more on consistency, and of course, I'm gonna walk you through examples. Okay, so excuse me, I need us to revisit the definition of consistent estimator again. If we have an unbiased estimator, okay, an unbiased estimator is actually, said to be consistent estimator of the population parameter theta, or if, when we take a sufficiently large sample, the variance of that estimator is going to be equal to 0. And of course, if the estimator is a biased one, okay, so the variance here will be replaced by mean square error. So, of course, whether we are dealing with the unbiased estimator or biased estimator, of course, we're going to be um, looking at the limits of the variance and the mean square error, depending on, which of the estimator we are actually considering. And of course, in my last class, I told you that the knowledge of the idea of Chebyshev inequality is actually going to be used in consistency, because the reason being that the moment the variance has entered to infinity, and if the variance actually converts to 0, that implies our estimator will converge to the population parameter within a certain threshold. And of course, when you take a look at what I'm trying to show right now, Okay, I'm actually assuming that I'm focusing on unbiased estimator. Okay, that was why we got standard deviation. Okay, the standard deviation that we got is actually the square root of the variance of the estimator. So if the focus is on the mean square error, of course, the standard deviation of the estimator is actually going to be replaced, by the square root of the mean square error of the estimator. Okay, I need you to take notes of that. Okay, so in my last class, I was able to show that the probability of this convergence will approach 1 as in 10 to infinity. Okay, so if you follow what we did in class, of course, you know, the if you take a look at this guy and this guy, then you basically gonna see that my epsilon now, so what we call the epsilon is actually k standard deviation, of the theta curve. Okay, which is the estimator. So, of course, in that situation, I can figure out, okay, of course, when we're dealing with the Chebyshev inequality or the other time, the moment we figure out K, of course, we can calculate the probability of the convergence. Okay, so we're gonna plug in K here. Of course, by the time we plug in that guy, we're actually gonna have this. And the moment we got that, the square of the standard deviation is gonna be a variance by the time you actually have algebraic simplification. We're actually going to have this guy. And of course, if you want to go by the definition of consistency, okay, by the time n tends to infinity, of course, the sample, the probability of the convergence now, the probability, that the estimator will converge to the population parameter value within a certain threshold, that probability converges to 1. So that's exactly what we mean. Okay, so I want to go into example now. Okay, in the last class, I actually show you how we can investigate, the what we call the consistent property of an estimator. So if estimator is actually unbiased, we're gonna need to derive an expression for the variance of that estimator, and of course, we need to tend n to infinity. Okay, so just like the definition that we have here. Okay, so now we want to talk about variance, the sample variance. Of course, before now, I've already proved that the sample variance is an unbiased estimator of population variance. Of course, we've proved this guy before, so which actually implies that the sample variance is an unbiased estimator. Okay, so if the sample variance are unbiased estimator, so it becomes necessary to investigate its consistency. So if I want to investigate the consistency of the sample variance now, what I'm actually going to do is to derive an expression for the variance of the sample variance. If you remember the idea of a sampling distribution, okay, if I want to figure out the sample variance, from a given observations, of course, or let me just say we go into population, we take a sample of maybe 20, and we want to figure out the sample variance. Okay, I'm gonna say if 1,000 investigators should go into the same population and they choose the same sample size, okay, and they compute the sample variance, of course, they're gonna get different results, even though they are working on the same team. Okay, of course, we know there's sampling variation. Okay, now because of that, the sample variance becomes a random variable, and when it becomes a random variable, of course, it means it varies, and we can decide to compute the variance of the sample variance. Okay, so now if we want to actually prove that, so I think I'm going to share my whiteboard now. Okay, I'm going to share my whiteboard now. Okay, I'm actually going to share my whiteboard. Okay, so we take a look at my whiteboard now. Okay, we take a look at my whiteboard now. Okay, so we actually have a sample variance, which is summation y minus y bar squared. Okay, divided by n minus 1. Of course, we've been able to show that the expectation of the sample variance is that. Okay, so if I want to investigate consistency now, then then I need to be able to get expression for the variance of sigma squared. I have an expression for the variance of sample variance. Okay, so if I want to derive an expression for the variance of sample variance, okay, so we actually need to use what I call the knowledge of statistical theory. Okay, in the knowledge of statistical theory, if I have n minus 1, okay, sample variance, divided by population variance, okay, so this guy is actually distributed chi-squared with n minus 1 degree of freedom. Okay, so in that situation, we need to be able to recall, the property of chi-square distribution. We talk about the mean of a chi-square, the variance of a chi-square. Of course, from statistical theory, the mean of a chi-square, the expectation of a chi-square, okay, is actually going to be equal to the number of degree of freedom, and of course, the variance of a chi-squared, okay, from statistical theory, okay, is actually going to be 2 into it's going to be 2 times the degree of freedom. Okay, so I'm actually going to use the idea now. Okay, so using the idea now, so I can actually which means I'm going to write the variance of into n minus 1, okay, this, okay, like I said, equal to 2 into n minus 1, because we're using the idea from statistical theory. What you got in the parentheses right now is actually a chi-square, okay, chi-square statistic, and of course the variance of a chi-square is actually 2 times the degree of freedom. Okay, so the next thing we're gonna do now, okay, in the parentheses, the constant is gonna be n minus 1 and the sigma squared, and of course we know the estimator is the sample variance, okay, which actually varies. So I'm actually gonna have n minus 1 squared, okay, sigma raised to power 4, okay, because this is gonna come out squared, right? And I'm actually gonna have the variance of sample variance, which is equal to 2 into n minus 1. And of course, this is what we're looking for. Okay, so the variance of sample variance now is actually going to be 2 into n minus 1, or sigma raised to power 4 divided by n minus 1, n minus 1 squared. Okay, so we'll take a look at what I have now. So this guy is going to reduce that. And of course, we're actually going to have 2 sigma raised to power 4 divided by n minus 1. So anywhere in the world, the expression for the variance of sample variance now is actually 2 sigma raised to power 4, divided by n minus 1. Okay, so, and, the moment we take the limit, okay, as n tends to infinity now. And you can see that the n occupy the denominator position. We actually expect, that expression to converge to zero. Okay, so the implication now, the takeaway now, okay, since that's the variance of sample variance, with an estimator here actually converges to zero, the conclusion is going to be, the sample variance is consistent. Okay, so which is one of the reason why in statistical analysis, if we are given a sample of data, you want to figure out, the sample you want to compute, or you want to compute, the sample variance, we actually going to use, this because sample variance as an estimator, is unbiased, and not only that, is consistent. If you follow what we did right now. Okay, so I'm gonna stop my share, and I'm actually gonna go back, to the lecture material. Okay, give me 1 second. I'm gonna share the lecture material now. Okay, so if you take a look at I think I've just demonstrated, that, I just showed that the sample variance, is actually a consistent. Okay, so another information that I would just wanted to see is this. The first movement is that, the second movement. Okay, we got the third movement, and this is the fourth movement. Okay, so you know, all those have to exist, okay, for us to be able to compute the variance of the sample variance. Okay, don't forget the other time, the expression that we got for this variance of the sample variance was actually 2 into, I think, give me 1 second, 2 into, that's going to be variance, okay, of this is going to be 2 into sigma 4, okay, ratio divided by n minus 1. Okay, and of course, when you take a look at sigma raised to power 4, of course, there's possibility we actually going to be needing up to 4 moments. Okay, so I'm gonna move right now. Okay, we also have another. I think I've shown you all this before, but I'm gonna talk about this guy now. Okay, because in the process of investigating, the consistency of sample variance, we also need to take into consideration, the formula for the variance of y, random variable y, is actually this, and of course the expected value of y squared. Okay, is if you take a look at this guy now, okay, this guy is actually this guy, okay, and this guy is actually this guy, and it has to be defined, it has to be determinate. So that was why you see that the difference of that has to be less than infinity. Okay, and you know what, if the variance of y equal to that, okay, the variance of y raised to power 2. Okay, so the variance of y raised to power 2. So it's more or less like you squaring what you have inside the parentheses, and that was why you got this guy now. That and this guy here is actually this, and this guy here is actually this, and you know what? That's also need to be defined. That was why we got less than infinity. And of course, if you want to put into consideration the weak law of large number. Okay, so if I want to obtain the expected value of y, okay, so we actually, the expected value of y here is going to be population parameter in a way, okay, and we believe that if I have data set, okay, and so a sufficiently large sample, and using the idea of weak law of large number, we expect that summation y over n is actually this guy here. Okay, and that very convergence take place in probability. Okay, now um the same thing also applicable to if I want to figure out expected value. Okay, expected value of y squared. Okay, so of course the expected value of y squared, so 1 over n summation y squared also converges to that, and that is the reason why if I want to figure out how expected value of y squared, which is the second moment from the data set, okay, I'm actually going to do summation y squared divided by n, which is going to be the second moment. Okay, so with the theorem that I walked you through before, so let's say we got g of s equal to s squared. Okay, if g of s equal to s squared, and of course the fact that this converges to this, no, that is more or less like y bar converges to mu, okay, in probability. And if I want to apply Silovsky theorem now, okay, in Silovsky theorem, when a particular variable converges, another variable converges, if we try to multiply them, the product is going to converge. And not only that, whatever algebraic operation we perform, on the two variables, that actually converge on their own, of course, that we all the product is also going to, the result is also going to converge as well. So in a situation where this happen, of course, we can actually say y bar squared, okay, also converges to the mu squared. Okay, so which means we're actually using Silovsky theorem here. Okay, if y bar converges to mu, we actually expect the y bar squared to converge to mu squared. Okay, that is exactly what we're trying to say. If we are working with something that look like a quadratic function. Okay, so in the end, you're actually gonna be able to have a way of getting the variance of y. If I want to get the variance of y from the sample data, of course, I know the estimator to use. Okay, and of course, before now, so I've already I'll show everyone in the class, how the expected value of the sample variance is going to be population variance. But let me tell you this, um, at very large sample, we expect that the sample variance is actually going to converge to the population variance. If you take a look at what we have right now, okay, or if you take a look at this guy now, okay, that's another way, initially we got summation y minus y bar squared divided by n minus 1. So when you take a look at this guy, it's actually the same thing as this guy here. Okay, by the time you expand that, that is what you're gonna have. Okay, and if that guy now actually is going to converge in probability, because when you take a look at this guy now, for sufficiently last sample, that is going to be 1. And of course, when you take a look at this guy, that is going to be the sigma squared. Okay, that's going to be the sigma squared. Okay, so why is it sigma squared? Don't forget, we are using the facts that we've already said. Okay, if I want to analyze this guy for you, you're gonna know that I said, the y bar squared actually converges to mu squared. Okay, and then so if it converges to mu squared, okay, and the mu squared is more or less like expectation of y or squared, right? And when you take a look at the other part, okay, the summation y squared over n, we said it the other time, that we converges to expected value of y squared, of course, and you already know that the variance of y, okay, is actually going to be equal to that. So in a way, so that was why we said that that guy here is going to be sigma squared. And at the end of the day, multiplying sigma squared by 1, you got sigma squared. Okay, so what is the implication? Okay, of course, when the convergence takes place, of course, or the statistical inference, that we conducted the other time. When I say statistical inference, constructing confidence interval or testing hypothesis about parameter. But in this class, I've walked you through how we construct the confidence interval. So, the confidence intervals actually become possible because of the fact that we got assumption that estimator we converge to their true parameter value. So when you take a look at what I have here, the common estimate, the common parameters, okay, when you take a look at all this guy, we got common estimators that converge to them. Okay, if you check, what we did, before now, and of course, by central limit theorem, if an estimator is approximately normal with a mean of theta and the variance of that, okay, we can now construct a confidence interval. Okay, now the confidence interval, because you are seeing Z, it's actually going to be large sample confidence or interval. Okay, all that happen as a result, of the fact that convergence actually takes place. Okay, so and if that happen, then we can begin, it should be reasonable to also assume that if I look at the difference between you know the ratio, the difference between the when I divide the difference between estimator and the parameter by the standard deviation of the estimator, okay, that is actually going to follow standard normal distribution with the mean zero variance one. Okay, or we can force that to follow that. The only way to force that to follow that is when we take a sufficiently large sample. And of course, that convergence here is actually going to be called convergence in distribution, because initially that estimator, okay, was from it has a CDF, the cumulative distribution function of a different distribution. But you know what, at a very last sample, it becomes the cumulative distribution of a normal distribution. Okay, so and looking at this Silosky theorem, suppose we got UN, has a distribution function, okay, that converges to a standard normal distribution as and becomes sufficiently large, and it becomes sufficiently large, so when n tends to infinity. Okay, so we want to define a WN, okay, or let's say WN converges to probability one, okay, and I want to figure out, I want to look at the ratio. Let me just say this again. We got two variables here that converges. UN converges, okay, um, you know, the UN converges to standard normal distribution, okay, as n's becomes sufficiently large, and WN converges to a constant, okay, it converges to a constant, okay, and you know what, I want to look at the ratio of the two variables that converges on their own, of course, by stochastic theorem. Of course, that is the ratio is going to converge as well. Okay, when you see because the denominator converges to one, the ratio of that, the UN, to me, the UN divided by WN is more or less going to be a UN. So which means the distribution of that convergence is not going to change. So what am I talking about? The distribution of UN is also going to be the distribution of UN divided by WN, because if you take a look at the statement here, if WN converges in probability to one, okay, that's what we mean. Okay, so, and that was why mathematically speaking now, okay, if UN sequence so converges to standard normal distribution, as n becomes sufficiently large, okay, what we can say for every x in real number now, okay, the limit as n tend to infinity, the probability of UN, let's say equal to x, okay, that is actually going to give you the cumulative distribution function of a standard normal. Okay, that's what we mean. Okay, that's what I mean. Okay, so we're gonna go into another example now. Suppose that y1 up to yn is a random sample size, the random sample of size n from a distribution. The mean exists, the variance exists as well. And of course, you define a sample variance, because this is sample variance, right? And we want to show the distribution function now of this guy converges to a standard normal distribution. There's something I want to take note, to take a look at this guy is just the square root of the sample variance. Okay, so let me tell you this. If the sample variance converges to uh population variance, then I also want to believe that the sample standard deviation is also going to converge to population standard deviation. Okay, so that's exactly what I mean. Of course, using Skoletsky theorem, and that is actually going to happen. Now, what we want to do now, is to investigate the convergence of this guy now. Okay, so if I want to investigate the convergence of that guy, because I'm actually going to call that UN. Okay, so when I call that UN, okay, so if you go back, if you want to rearrange this guy, okay, you're actually gonna have, okay, let's all first try by defining UN to be that. If you go back, you're actually gonna see, this is what we want to investigate. But you know what? We know from central limit theorem, when UN equal to that by central limit theorem, we actually expect UN to actually follow standard normal distribution with a mean zero variance one. That is if and only if the sample variance is large. Okay, so if I want to go by Selesky theorem, where Sn converges to population standard deviation, of course, the Wn here is actually going to converge to one. Okay, because when Sn converges to sigma, okay, you're all just going to have a sigma divided by sigma, and under a sufficiently large sample, we actually expect Wn, of course, to converges to one. That's what I said the other time. Okay, so this is the theorem. We proved that the other time. The sample variance converges to population variance, and we also expect the sample standard deviation to converge to population standard deviation. In that situation, the Wn, of course, going to converge to one in probability. Okay, so if you take a look, if I have a g of x, which is defined as a square root of x, divided by sigma, okay, and of course, we actually want to figure out the g of the sample variance, okay, so which means wherever I see x now, it's going to be replaced by sample variance. Don't forget, the sample variance also is a statistic, it's something that varies. Okay, now we take a look at this guy now. At the end of the day, take a square root of the sample variance, that's going to be Sn. And you know what, when Xn, the sample standard deviation, is going to converge to population standard deviation in probability, for a sufficiently large sample size. Because of that, this is going to give you one. Okay, it's going to give you one, and one can conclude that the Wn actually converges to one in probability. Okay, so so let's get theorem again. Okay, if I have this guy now, okay, where this is Un, okay, divided by Wn, okay, this is actually going to be, what you were given, that's what you're given initially. You see now, I'm talking about this guy. That was what you're given initially. Okay, that was what you're given initially. Take a look at that. Okay, now, then we're gonna say the distribution of that is still going to be standard normal. because the WN is acting like one because it's going to convert to one, as you can see here in probability. Okay, so far so good. Now I want to have remarks now. So the moment the convergence, of that actually take place, the implication of that is that this guy being an estimator now, we can now construct confidence interval on that. And that was what we did, some lectures back, and we were able to use that we're able to construct that as a confidence interval to figure out, if you really want to actually construct a confidence interval that is going to base on the mean. Okay, we've done that before. So the implication is that, we have this guy in place because of the convergence that we actually believe has taken place. Okay, so want to go into another example now. Suppose y1 up to yn, okay, follow Bernoulli distribution IID. Okay, of course, we know from statistical theory the variance of y is in Bernoulli is going to be p into 1 minus p. Okay, and of course, the expected value of y is going to be equal to p. Don't forget, Bernoulli distribution is a probability distribution used to model random variable that have two possible outcomes. Okay, so that's about that. Okay, so and don't forget in class I also told you pick up sample proportion, or the estimator for proportion is also the same as the y bar. Okay, don't forget, if this y1 up to yn, let's say we want to investigate how many American citizen approve the job the President Biden is actually doing. Okay, of course, I expect, you know, there are two possible responses. Either they say yes or no. Okay, yes, oh, I approve the job the president is doing. No, I don't approve that. And of course, I'm going to label Y1, HY as 1 and 0. Okay, 1 is going to be for yes, 0 is going to be for no. And of course, I'm interested in the totality of the numbers of yes. Okay, that's going to be summation y. Okay, and that summation y is going to follow binomial distribution. Okay, when summation y follow binomial distribution, which is the totality of the numbers of yeses right now, then we can actually figure out the average of that. Okay, the average of that is when you divide by n. So that's why the p cap now is actually sample mean. Okay, so if I want to go back to the UN that I talked about the other time, okay, initially we're focusing on the sample mean, and what we're trying to do is to plug in the proportion now. Okay, we're actually gonna have this guy, we plug in the KPK, which is the sample proportion, and the P, which is the population proportion. And of course, what you're going to see in the denominator is actually going to be the standard deviation of the sample proportion. Of course, if I want to write this guy now, okay, if I want to write that, just going to be p cap minus p divided by square root, okay, of p cap, okay, 1 minus p cap, okay, all divided by n. Okay, so this guy here is the same thing as that guy, of course. For sufficiently large sample, we expect the whole expression to converges to standard normal distribution, as you can see. And if that happen, of course, if that happen, what we can do, we can the implication of that, we can also construct a confidence interval around the sample proportion, which is going to be this guy, which is what we've done before. Okay, now we want to go to another question now. So take a look at this question. Or can we use sample variance to estimate this? You know, that's it. When I'm talking about Bernoulli, okay, Bernoulli, we have, population variance. The population variance is the variance that the variance of a random variable that we derive from that particular distribution, which is this guy now. And as you can see, the P into 1 minus P. So the P here is a parameter, okay, which is a population parameter, which is a population value. Okay, now the question now, can we use a sample variance? If I want to compute the variance of y that follow Bernoulli distribution, so can we use a sample variance to do that? Okay, that is a question. And of course, yes, we can actually use a sample variance. Don't forget, sample variance as an it's an unbiased estimator, it's consistent, it's also efficient. We've already proved that, and I'm going to demonstrate that that we can actually use sample variance. Okay, so we're going to record the formula for sample variance, okay, which is that, right? And don't forget, the random variable y equals 0, 1, which is Bernoulli distribution, okay? And when I'm talking about Bernoulli distribution, there's something I needed to understand. Y is going to be the same as y squared. Don't forget, the state space is 0, 1. So when I square 0, I'm actually going to have 0. When I square 1, I'm still going to have 1. And that is the reason why y squared is going to be equal to y. Oh my God. What we're going to do now, the other time, don't forget, we said that expected value of y, okay, in place of expected value of y, y bar converges to that, okay, in probability. And don't also forget the y bar squared converges to expected, converges to y bar, the y bar squared converges to mu squared, okay. I needed to take notes of all of that. Okay, so if that happened, now for Bernoulli distribution, since we know that this guy equal to that, okay, and we know that the expected value of y for Bernoulli equal to p, okay. Now, what I'm trying to tell the world now, expectation now, oh my God, expectation of y squared is also going to be equal to p. So that is exactly what I'm trying to talk about here. And don't forget that we've already said that 1 all over n, give me 1 second. We've already said that this guy here actually converges to expectation of y squared in probability the other time. We said that, okay, and if that guy converges to that, okay, and this guy here, don't forget that is a sample mean, is going to converge to expected value of y in probability. I showed you the other time the takeaway now. If y squared equal to y because of the state space of y, okay, we're actually gonna say y bar equal to all of that equal to p cap. Okay, now what are we gonna do now? Okay, we want to plug in. Okay, here we know what is 1 over n summation y squared. That is gonna be a p cap, which is what we prove here. We're going to plug that in. And what about y bar squared? You don't forget, y bar is p cap. The y bar squared is going to be p cap squared. Now, when you take that was how we actually got this guy now. Okay, by the time we factorize this guy, now we're going to have this guy. So right now, the expression is going to be sample variance equal to that. Okay, when sample variance equal to that, what are we going to do? Moving forward, going back to the standard normal of version of that. Okay, now this guy now is actually going to be this. Okay, why is it that? So we actually are substituting, okay, for that, which is this. Okay, we're substituting for that. And how do we get that? If you go back, you're actually going to see, okay, if this guy equal to this guy, then xn, which is going to be the square root of all of that, it's going to be that over that p cap 1 minus p cap n. Take a look at that. So that was how we're able to arrive at this guy now. Okay, arriving at that guy now, when we do some simplification now, oh my God, I'm actually gonna have this guy. And when you take a look at that guy, it's actually gonna converge to standard normal distribution, which means the implication of that, we can actually construct the confidence interval about that. Okay, so some of you may be wondering, why do we need to construct confidence interval? Of course, I told you, you know, uh, previously in my lecture that the idea of the confidence interval is needed, for us to be able to have, really ability on the sample of proportion. Okay, so and at the same time, a point estimate could be wrong or right according to the classical approach of probability. Okay, oh my God, that's gonna be the last slide. Okay, I would appreciate everyone who have listened today. Make sure you stay safe and have a lovely day. Bye for now, everyone. See you in class tomorrow.